What specific problem does your research aim to address regarding the limitations of parameter-efficient fine-tuning methods like LoRA compared to full fine-tuning?
Our research addresses the limitations of parameter-efficient fine-tuning methods like LoRA by investigating the structural and behavioral differences between LoRA and full fine-tuning. We specifically highlight that LoRA introduces intruder dimensions, which are singular vectors that do not align with the pre-trained model's singular vectors, leading to a loss of spectral similarity and poorer generalization outside the adaptation task distribution. Additionally, we observe that LoRA fine-tuned models tend to forget more of the pre-training distribution and exhibit less robust continual learning compared to fully fine-tuned models. Our findings suggest that while LoRA can match the performance of full fine-tuning on specific tasks, it does so at the cost of introducing these intruder dimensions, which negatively impact the model's adaptability and performance on harder tasks. Ultimately, we propose that higher-rank LoRA models can mitigate some of these issues, but they still do not fully replicate the benefits of full fine-tuning.
Can you explain how the proposed method of using low-rank adaptation, LoRA, works? Illustrate this step by step, highlighting any key mathematical formulations involved in the training process.
Low-rank adaptation, LoRA, works by decomposing the weight update during fine-tuning into a product of two low-rank matrices, specifically, delta W equals BA, where B in math BB r M times R and A in math BB r times N \. This approach significantly reduces the number of trainable parameters compared to full fine-tuning, which updates the entire weight matrix, W_0, with delta W in math BB r M times N \. During the training process, B is initialized to 0, while A is sampled from an isotropic Gaussian distribution. The effective number of trainable parameters in LoRA is Mr plus Rn, which is much smaller than the Mn parameters in full fine-tuning, especially when R is much less than both M and N. Additionally, the scaling factor, alpha, is introduced in the prediction equation. Y equals W_tuned x equals W_0 plus frac alpha RBA x, where setting alpha equals 2R has been shown to improve results for higher ranks. This formulation allows LoRA to adapt the model to specific tasks while maintaining a lower computational cost and memory requirement, effectively leveraging the intrinsic low-rank structure of the updates needed for fine-tuning.
Could you provide a simple example that demonstrates the inner workings of the LoRA algorithm, including the role of matrices B and A in the adaptation process?
The LoRA algorithm adapts a pre-trained weight matrix, W_0, by introducing a low-rank update represented as delta W equals BA, where B and A are matrices of lower rank. Specifically, B is of size M times R and A is of size R times N, with R being significantly smaller than both M and N. During the adaptation process, B is initialized to 0 and A is sampled from an isotropic Gaussian distribution. The product, BA, effectively captures the necessary updates to the weights while maintaining a reduced number of trainable parameters, thus allowing for efficient fine-tuning. This low-rank representation enables the model to adapt to the downstream task while minimizing the computational burden, as only Mr plus Rn parameters are trained compared to the Mn parameters in full fine-tuning.
What are the theoretical or practical benefits of using your proposed LoRA method over traditional full fine-tuning, particularly in terms of computational efficiency and model performance?
The proposed LoRA method offers significant computational efficiency over traditional full fine-tuning by reducing the number of trainable parameters from Mn to Mr plus Rn, where R is the low rank, thus making it more feasible for larger pre-trained models. Practically, while LoRA can match the performance of full fine-tuning on certain tasks, it introduces fewer intruder dimensions, which are singular vectors that do not align with the pre-trained model structure, leading to better generalization outside the adaptation task distribution. Additionally, higher-rank LoRA models exhibit improved adaptability and generalization compared to lower-rank versions, suggesting that they can leverage more expressive power without the drawbacks of overfitting. The findings indicate that LoRA can achieve similar accuracy with less computational cost while maintaining a closer spectral similarity to the pre-trained model, which is crucial for continual learning scenarios. Overall, LoRA provides a balance between efficiency and performance, particularly in challenging tasks where full fine-tuning may struggle.
How did you validate or test the performance of the LoRA method? Please detail the experimental setup, datasets used, and metrics for assessing the effectiveness of the method.
To validate the performance of the LoRA method, we conducted experiments using the Roberta base model fine-tuned on 6 different sequence classification tasks. The models were trained to achieve similar performance levels on their respective downstream tasks, allowing for a direct comparison of the structural and behavioral differences between LoRA and full fine-tuning. We measured the total number of intruder dimensions in the fine-tuned models by applying singular value decomposition, SVD, to both the pre-trained and fine-tuned weights, assessing the cosine similarity of singular vectors to identify intruder dimensions. Additionally, we evaluated the model's performance in a continual learning environment, measuring how well they retained knowledge from previously learned tasks and their ability to generalize outside the adaptation task distribution. Metrics included accuracy on in-distribution test sets and pseudo-loss scores on pre-training data, which helped us analyze the model's forgetting behavior and generalization capabilities.
What significant results did you find in your experiments, and how do these outcomes compare with those obtained through full fine-tuning, particularly in terms of the concept of intruder dimensions?
In our experiments, we found that LoRA fine-tuned models consistently contain intruder dimensions, singular vectors with low cosine similarity to pre-trained singular vectors, while fully fine-tuned models do not exhibit such dimensions. Specifically, LoRA models with ranks up to 16 showed a significant presence of intruder dimensions, indicating that they introduce new singular vectors that disrupt the spectral properties of the pre-trained model. In contrast, full fine-tuning maintains a spectral similarity to the pre-trained weights, making smaller adjustments to existing singular vectors. This structural difference leads to behavioral discrepancies, as LoRA models with intruder dimensions tend to forget more of the pre-training distribution and exhibit less robust continual learning compared to fully fine-tuned models. Ultimately, while both methods can achieve similar performance on target tasks, the presence of intruder dimensions in LoRA models suggests a detrimental effect on their generalization capabilities outside the adaptation task distribution.